All right, in Physical Science 20, what we're going to be talking about today is a section of chemistry called Stoichiometry. And in this section, what we're going to be learning about is the area of chemistry that deals primarily with amounts of substances in chemical reactions. So that's what the meaning of stoichiometry is. It's the area of chemistry that deals with amounts of substances in chemical reactions. So we've been studying chemical reactions like, H2 plus O2, gives us water, and we've been able to balance that and, talk about the effects of, what category that reaction falls into, as a synthesis reaction and this sort of thing. So we talked about formulas, chemical reactions, balancing types, all that sort of stuff. We now need to talk about the reality of chemical reactions, so the amount of substances. So, for example, if we have a very simple equation, let's try this one. Super simple. Sodium ion plus chlorine ion produces sodium chloride. Okay. When we're talking about amounts of substances, and remember, when we balanced the equation, we talked about a recipe and how much of each ingredient you need to make something. And that's what balancing is. But what are the numbers really? And how do we determine, a mass of sodium and a mass of chlorine, and how much mass will it produce of this? And so that's what we're going to find out. We're going to use everything that we've been learning about, the equations, balancing, ratios of the ingredients, and also what we just got finished talking about was the mole concept and conversions, right? So you've been working on that, converting moles to grams and grams to moles and such. So we're going to put it all together in this section. It's very important where in industry, okay? So if we're making something, we're making a product, we need to know how much reactant is needed to not only make the product, but to efficiently make the product so there's no waste. You don't want to buy more reactant than you need. If it's really expensive, you only want to buy just what you need to make what your product. And so you don't want to spend too much money in that way. Also in the lab, when we're doing a lab experiment, you can determine how efficient your procedure was. And in Chemistry 30, next year, you do chemistry, if you're going to do Chemistry 30, which most of you probably are, we have a big lab towards the end of the semester, a solubility lab, and we do this. We actually measure out, mass of reactants, you react it, and then we collect the product, and you take the mass of the product, and then you determine how efficient your experiment was. So that's what we're going to do, in the next class. So these are the steps in solving stoichiometric problems. Okay, so here are the steps. First thing you want to do is you want to make sure that you balance the equation correctly. And it's also, you want to make sure that the equation is written correctly. So if we're talking about, silver sulfate, and you start off by going, okay, well, silver sulfate, and you look at the charge in silver, and it's a 1 plus, and you look at the charge in sulfate, it's a 2 minus. We have not correctly written this formula. So we have to go back to the very beginning and make sure that you write the formulas for everything involved correctly. So this should be Ag2SO4, right? And then we need to make sure that we balance. So it's correctly written, the equation, and it's balanced. This is very important because the numbers, and that is like these numbers right here, okay, when you're, balancing, blah, 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 the coefficients are actually called molar ratios. So this number really means, and we haven't really talked about what this number actually means other than just, how many sort of molecules or what's the ratio. It's actually a molar ratio, so we're talking about moles of silver sulfate. So it's a molar ratio. So those coefficients that we've been working so hard on you have to understand now, are the molar ratios of all the substances. So it's 1 mole of this plus, 2 moles of the second substance produces maybe 1 mole of this substance. Right? So these numbers are the ratio of moles of the substance. Very important. Okay, so, question? No. All right, step number 2. Determine moles of all the reactants given. So we are going to, in step number 2, determine the moles of all the reactants. As I mentioned, the coefficients in the chemical equations are molar ratios. It's important to note that they are not ratios of mass. That is super, super important. And I think once students understand this pretty well, hasn't been a real tricky spot in previous years that I've taught this. Students understand that we have to convert to moles first, and I preach that over and over. If you're given mass of reactants, we need to convert to moles. So that's why step 2 is determine moles. We have to convert everything to moles first. If we're given, the number of molecules, we have to go to moles always. If we're given the mass, we have to go to moles always. We're always dealing with moles. Okay? So that's step number 2. Convert everything to moles. Now, just a side note here. For most questions that we're going to do, one reactant is given. So we're given a mass maybe of, let's say, this silver sulfate. And then the other reactants, or the one other reactant that it's reacting with, is usually said to be, we have lots of it. We have a little bit of extra of this. And I'm going to talk more about this later. But we are sort of running out of time in this, in this semester here, so we'll see how far we get. But there are, most of the times you'll be given one mass only, and it'll be said that the other reactants are given in excess. So that means there's lots of them to react, so you have to focus on just the mass that's given. So you'll understand that more as we do problems. Okay. Step number 3. And like I say, we're going to get these rules down, and once we actually start doing them and you refer back to them, they'll make a little bit more sense once we actually use them. But I thought, let's just kind of get some ground rules here, and so you can jot something down. So step number 3 is determine the amount of moles of desired product. So most of the time, these questions are, I'm giving you this much of reactant A. If this all reacts according to the balanced chemical equation, how much product should you get? That's what the question is going to be like. Here's the reactant, here's the equation, now tell me how much product you're going to get out of it. Okay? So what we have to do then is we have to determine how many moles of the product that we're going to get. And of course we have to use the coefficients, which are the molar ratios of the balanced equation. So if reactant A and product A are in a 1-to-2 ratio from the balanced equation, then obviously 1 mole of reactant A is going to produce 2 moles of the product. So we take the number of moles of reactant A and we multiply it by 2. It's pretty easy. And I'm going to do just a little kind of sample here with you in a second. Okay? So just get that copied down, and we use the molar ratio in this way. Okay. So let's take a look at an example here, and let's run through all of the steps, 1 to 3 so far. Okay? So I am suggesting that we're going to deal with this equation here. Now, what's step number 1? Says that we need to have a balanced and correctly written chemical equation to start. So in this situation, we've got hydrogen combining with oxygen to form water. Now, A, is everything written correctly? And B, is it balanced? Thank you. Very, very good. Oxygen is one of the diatomic 7. Good job. So we've noticed that this should be O2. All right, so step number 1. Make sure that you've written the chemical formulas of all the substances correctly. Okay, good catch over here. Now, what's next? Are we balanced? Is this a balanced equation now? Well, we check hydrogen. Hydrogen seems to be good. 2 here, 2 here. We check oxygen, and we go, oh, we've got 2 on one side and 1 over here. Now, you should have done enough practice here now on this to know what to do. You want to give it a try? Okay, yes, very good. First step might be to recognize that we have 1 over here and 2 over there. And so the first step might be to say, I only need half of those. Okay, we talked about that as a first step. You totally could do that. Now, are we done, or do we have to do one more thing? And right, you have to now multiply everything by 2 because we don't really want fractions as coefficients. Very good, very good. And some of you may have said, and knowing that we're going to do those 2 steps, some of you may have just said, you know what, I'm going to multiply this by 2 to balance the O's and this by 2, and we're done. Put a 1 there, we're done. And that's exactly what you get if you did that fraction first, okay? So, awesome. Step 1, we've got correctly written formulas that change that O to O2, and now we're balanced, right? Okay, what about step 2? What does it say again? Step 2 says determine moles of all reactants given. Okay, so in this example, I am going to say that we have 2.5 moles of H2, and we have oxygen is in excess, so we have an excessive amount of oxygen. All right. Now, when it says determine, you may have to calculate moles if we're given mass or if we're given number of molecules, right? That's the assignment that you guys are working on also here. So I'm just, for this example, I'm just going to say we have 2.5 moles. Okay? So we've got that, and we want to determine the number of moles of desired product and use the coefficients in the equation. So what that means is how many moles of water, how many moles of water should I expect to be produced in this equation given this right here? How many? All right, now we hesitate a little bit, so let me talk about it. We've never really talked about it. I just wanted to see if you... Okay, someone says 5. Okay, you agree with 5? Isn't it supposed to be times 2? Is it always 1 to 2 ratio? Well, it's not always 1 to 2. You have to look at the equation. Okay, so we're given moles of H2, and we want moles of water. So you look at the numbers, the coefficients from the balanced equation. So in this case, in the example before, it was 1 to 2, yes. But in this example, all right, it's a 2 to 2. See that? So, I think I heard someone say it. We should expect, because it's a 2 to 2 ratio, we should expect the exact same number of moles. Because it's a 2 to 2 ratio. Make sense? 2 to 2, 1 to 1, the same. Okay? That's pretty easy, right? Really easy. Very, very easy. So, if I was given, let's say, okay, now you don't have to write this down, but now I'm going to change this. And I'm going to say, just to see if you understand, I'm going to say, now we're given 3.8 moles of oxygen gas. How many moles of water would I expect to be produced? How many moles? Remember, and this is molar ratio. So what do we have now? We have 1 to 2. So guess what? I should expect twice as many moles here. Okay? So what is it? 7.6 moles. Very good. Do you guys understand that? Okay? Now, what happens, and I'm going to give you another example here. So you might want to just make some space for this. I'm going to erase this one because you guys totally understand that one. Okay? So here's one more, and this one's going to be a bit trickier. But I'm just going to make this up. So 2A, whatever A is, doesn't matter, plus 3B produces 5C. You know what? Forget that. We'll stop. I don't want to make you think something that's not true. I'm going to say 3 here. No, I'm not going to say 3 either. Sorry. I'm going to say 7. Oh, let's just go way out on a limb. Now, the reason why I didn't want to put 5 is because, now listen very carefully, some students think this as well. They think, Mr. Maxwell, I know math, and this is pretty much a math equation, so if I have 2 moles and I'm added 3 moles, I have 5 moles over here. Can I tell you, in chemistry, that is not the case. It is not a simple addition statement. That's why I didn't want 5 here, because you look at that and someone might say, yeah, 2 plus 3 is 5, no problem. Not the case. And why is that? Because remember, this is moles, not mass. You can have different number of moles on either side, right? And in all of the balance equations that we've done, if you look back and you notice, there's not very many where you add up the numbers and they're the same on both sides. So that does not have to happen in chemistry, okay? Because it's moles, not mass. And that might make a little bit more sense as we move through all this, okay? But anyway, so let's say it's 237. Now, let's say that I'm given, okay, 1.5 moles of A, and I've got an excessive amount of B, so we don't have to worry about B. That's not going to kind of restrict what's happening here. But all of these moles are going to react, and I want to know how many moles of C would I get. Now, the ratio, right, is 2 to 7. Now, it's not as easy as 2 to 4. Like, you can't just multiply by 2. And you might say, oh, I know what I multiply by, Mr. Maxwell. I multiply by 3.5 to get 7. But what if you didn't know that number? How would you do it? Here's a little trick, okay? If you want to go from 1.5 to blank, and you know you have 2 to 7, here's one thing that students really, it's easy to remember, and this is the one that they use most. There's different ways you could view it. But this is what I do. This is 2 to 7, so guess what? We're going to go 1.5, that's what we're given, and we're going to multiply by this number, the one that I'm going to, 7, divided by 2. 2. Why did I write 7? 7 over 2. So I'm going to this one, so I write this number. I'm coming from this one, I write this number. That's just an easy way. That works every time. Every time. And if you do that, then you go 1.5 times 7, all divided by 2, which is the same as doing 3.5, right? 7 over 2 is 3.5. So once my calculator comes up here, I'll show you exactly how you can do that. On, clear, quit. Okay, 1.5 times times 7 divided by 2 equals 5.25. Now that is the same ratio as 2 to 7. 1.5 to 5.25 is the same ratio as 2 to 7. Okay, so another way you could look at this, and here's just another way some students like this too. You go 2 is to 7 as 1.5 is to the unknown x. And you could write as a ratio 2. And so you cross multiply, you got 2x equals 7 times 1.5, which is what, 10.5, divide by 2, divide by 2. A little more math, okay? But you should get the exact same thing. Okay? So two kind of different ways to look at that. Now, that's a tricky part. If you guys can kind of understand that, boom, you're halfway there. All right? Any questions so far? Because we're kind of getting close to being done this lesson, so you're probably thankful for that. Now, this is sort of the last thing I want to talk to you about, but it's sort of the beginning of how to do the whole question. So we're going to put everything together now. And step number 4 says that most stoichiometric problems, they ask for mass of product or products. So we do need to convert everything to moles at the beginning, but then at the very end, we convert to mass. So we convert to moles first, and then we convert to mass by multiplying by grams per mole. And I just say, remember that little chart that we drew yesterday in class. Okay, so that's the only other thing. There may be a conversion from grams to moles on both sides of the equation. So initially, and maybe at the end as well. Okay, sorry, you guys got that down? Now, here's just an aside. If representative particles are asked for, then we simply convert moles to representative particles by multiplying by Avogadro's number. And you remember how to do that. And what I'll do is I'll just So just give me 1 second here, okay? So if we go back to this moles, where was that conversion chart? Yeah, right here. See that? That's what I'm talking about, this one. Mass to moles divided by grams per mole. If you're going to go from moles up to mass, you multiply by grams per mole. So those kind of conversions we might have to do in stoichiometry, and also moles to representative particles and so on and back. So that's what I'm talking about. Okay, so back to this. So I'm going to give you a little flow chart, and honestly, I've found that this works the absolute best to do this flow chart. So I tell you what, write this down first. This is your equation, and then I'll talk about this. Okay, so I am going to ask you to basically write this flow chart for every stoichiometry question that you do. Okay? Trust me, this is not going to be a real hassle for you. This is going to help you organize everything. And I wish that my teacher would have showed me a flow chart like this when I was going to school. And maybe he did, and maybe I just don't remember it, and maybe I wasn't paying attention. But this works really, really, really well. So we've got the equation, and if you're given mass, you want to write that underneath the reactant that it's given. Okay? So you write down the mass here. Then what you're going to do is you're going to draw this arrow, and over here on the side, you're going to actually take the mass that you're given and divide it by the grams per mole of this reactant. So you're going to make that conversion. And you're actually going to show it in this area right here. So I can see and you can see what you're doing. When you convert to moles, you're going to write the number of moles right here in this line. Okay? So you've got your given, an arrow, and here's the mole. Okay? Once you get there, generally what we want to do is we want to find out how much product. So you're going to go from moles of reactant over here to moles of the product that you are looking for. And how do you do that? Well, you multiply by the molar ratio of the two. Okay? And that's the product coefficient. So that's, this one here. Let's say it's 2, and this is a 3. So the product coefficient would be 2, and the reactant coefficient is on the bottom, right? So it's 2 over what? 3. So that would be the example here. And then you write the answer over here. Again, on a line, right underneath where the product is. So keep them in vertical columns like this. Everything will be nice and neat and very predictable. And you can see what you've done. And I can see what you've done. Okay? So then finally, if you're asked for mass of the product, then you just do one more step. You draw this arrow, and over here you show your work. You multiply the moles multiplied by grams per mole of this formula. And then your answer goes there, and you can simply, I'll let you just kind of circle your answer here, and boom, you're done. If you need to rewrite it with sig figs or anything like that, then you can do that on the side or somewhere else and circle it. But usually you can just put your answer there. Okay? So it's a bit of a flow chart, and I'm going to demonstrate this for you, but that's sort of how I want you to do it. Now, a couple notes, just from years of teaching, there's a couple notes here that I want to put down. When you're determining grams per mole, please remember you never include the coefficients in the equation when you're determining that. Lots of students do this. And what I mean, for example, I guess I have it here. Yeah. You see, if you have NH3 as a product, for example, but in the equation you see that it's 2 NH3 like that, okay? So you have this molar, you have this coefficient here. So you don't do this. You don't multiply the grams per mole of NH3 by 2. You don't include this, okay? Don't do that. You just focus on what the compound is, and you add up accordingly. All right? So when you're finding grams per mole, don't multiply by the coefficient. That's not included. Questions? All right, we're going to do a sample problem here. And in your textbooks, which you don't have textbooks right now, right? We don't have this textbook here with you. Okay, no problem. So I'm going to get you to write this down. Okay, this is sort of our example sample problem here. And in the chemistry textbook, it's on page 233, Mineral Chemistry 30, but you guys don't have those with you for this section. So this is what the problem states, okay? And again, I'll have to just adjust this, but it says, find the grams of silver chloride. So you can just say, find grams of AgCl, and what you're given. So these are just the notes from what the problem would state in the textbook. You're given 17.0 grams of AgNO3. Okay, so find grams of AgCl. You're given 17.0 grams of NaO3, and the question actually says it is reacting with an excess of NaCl. So that's why I have lots plus NaCl. And here's the equation. Okay, so you can write down this equation. It's AgNO3 plus NaCl produces AgCl plus NaO3. So everything that I've highlighted, please write that down. I'll give you a second to do that, and then we'll continue. Here's the actual question from the textbook. It says, how many grams of silver chloride can be produced from the reaction of 17.0 grams of silver nitrate with excess sodium chloride solution? So that's what the actual question says. Sorry, I don't have it there, but these are your notes, and here's your equation. Okay, so what we want to do, first of all, is make sure that we have a balanced, properly written chemical equation. So if we take our look at our N, and I've done some of this work for you already, okay? So Ag, we have 1 and 1, Cl, 1 and 1, Na, 1 and 1, NO3, NO3. Okay, so the ratio is 1 to 1 to 1 to 1. This is a super simple one. This is going to be easy. All right, so if we do our flow chart, and for some reason we do have some things missing, but I'm going to help you out here. So what you're going to do is you're going to write what you're given underneath the proper compound. So we've got 17.0 grams. So I would suggest you write that underneath Ag. Okay, so do that right away, 17 grams. And actually, it would probably be a good idea to say, okay, here's AgCl. That's what I'm asked to find. So I'm going to put a line underneath here, and I'm going to remind myself that I'm asking, it says how many grams. So this is what I would do. I would write this line under here next and say, remember, this is where I'm going to. All right, so what I need to do is I need to draw this arrow and convert to moles of AgNO3. And how do I do that? Okay, well, in this little area here, I'm going to convert to moles by taking the mass that I'm given, so this mass, and I'm going to divide it by the sum of all of the pieces of this compound, right? So Ag, what's that? 107.868. Sorry, this didn't copy very well. Plus 1 nitrogen, so that's 14.00674, plus 3 oxygens. 3 times 15.9994. Okay, so take a moment and write that down. Do that on your calculator. Let's see if we all get the same answer, because, again, using your calculator properly is really important, so just practice that right now. When you do this, I get 0.100074797. You may have something really different way back over here. That's fine. Leave this whole thing, because remember, we're going to have to adjust for sig figs at the very end. So if you have some different number way back here, no problem. All right, so we're going to write that down, 0.10007. You don't have to write all the decimal places in your work, but please try and keep them all on the screen of your calculator so that we can use those, right? Be as precise as possible. So now what we're going to do, according to our flow chart, is we're going to now convert to moles of the product that we're looking for. So this should say moles of AgCl. That's what I want. And how do I do that? I take this number, and I multiply by 1 over 1. See, they're the same. It's a 1-to-1 ratio, so I multiply by 1 over 1. That whole ratio trick here always works. If it's 1-to-1 or 2-to-2 or 2-to-4, even the easy stuff, that always works. So, guess what? 0.1007, and you can write all the decimals if you want. Does everyone see that so far? I know this is getting a bit messy up on the screen, and this is what your work will end up looking like, but as long as you take it one step at a time, you should be totally fine. We're good? Yes, you're sure? Okay. I see some puzzled faces, but is that you're just absorbing, just processing the information? Okay. All right, you may have questions later. Okay, so now, from this step, I need to go up to grams of AgCl. Okay? Was there a question or no? So I multiply, I take this number, 0.1007, and all of its decimal places on my calculator right here, and I'm going to multiply by the grams per mole of AgCl. Okay? Because now we're talking about moles of AgCl going to grams of AgCl. So I take this number of moles of AgCl and I multiply by the grams per mole of silver chloride. And so that's the 107 times, 0.868 plus 35.4527. So I'm going to take my answer and I'm going to multiply by, I'm going to use my brackets here and add it all up. And I'm going to get the number of grams of AgCl that this number of moles represents. So 0.1 moles is 14.34 grams. So actually it's 14.34, 27899, but so on. What do I want to do for significant figures? And again, for stoichiometry, yeah, let's go with sig figs. How many sig figs am I given in my question? 3. Now the other sig figs, as far as mass for the elements, there's always lots of sig figs, right? 5, 6, 7. So you don't have to worry. What you're going to look at is what you're given in the question, and your answer should reflect those sig figs. So this one is going to be for an answer. I guess I've got sort of down here. So it's going to be 14.3 grams of AgCl. So that's going to be my final solution there. And you just did a stoichiometry question. Congratulations. All right. Yeah, I know that's a bit messy, but you know what? You're going to be all right. Okay, so that's the stoichiometry lesson there in a nutshell. And of course, we're going to be adding some variations, but there's the steps, there's a little flowchart you want to create, and there's the sample problem. So we'll do some more problems there, but that's kind of your lesson there for today.